Okay, good afternoon, everyone. I hope you're doing great. We are going to continue our journey. Now it's the time to focus on using data augmentation. I quickly go through this part because we have already talked about data augmentation. So overfitting is caused by having too few samples to learn from, and that is why we use data augmentation. And the data augmentation takes the approach of generating more training data for existing training samples by augmenting the samples via a number of random transformations that yield believable looking images. What does it mean, yield believable looking images? It means that if I show you, I have provided some links for that augmentation. And this is one of the amazing websites. Let me just bring the other one as well and show you a few points that I found interesting in these two. At the beginning, it starts defining the definition of augmentation. But look, we have a nice cat here, and we tilt it. If you see, the head is towards left in this picture, but if you see in the other one, it's towards right. It looks the other way, right? In this one that I'm pointing. So it's like flip horizontally. And in many of them, you see, for instance, here we have zooming. In this one, we zoomed out and we tilted. And there are other shapes. But I want to ask you, in this very digit, number 6, do you think that all those transformations are, I'm sorry, I've forgotten to share this with you, but look at this one. In this number, in this digit, guys, do you think that this one is a good kind of transformation? Yes or no? We generated like 20 images out of one single image, right? But do you think that this is all of them are acceptable or good? Look, if I take this one, that's a simple question. If I take this one and I'm gonna bring it to a place like Paint. And I'm gonna say this is the number, right? Tell me, if I say, let's flip it vertically and let's flip it horizontally, what is this number? So is it acceptable to do these two on this number? Nicholas, do you think that it is acceptable? The label for this number is what? The label is number 6, right? Let me bring it to another environment for you. And actually, I have provided something for this specific session. That's it. Look at this one. Imagine that I have something like this, number 6. The augmentation means accept this one, also accept this one, right? Accept this one, accept this one, zoom in, zoom out. If it is like this, and if the frame that our number exists is, I'm sorry, let me just bring it down. Okay. If this is the frame, it means that I can accept this one. If I can shift towards left or towards right or up or down or tilt, all of them are acceptable, right? It enhances, Jeffrey, and if it enhances what? The other numbers that could be written differently, and I can accept them because it looks like more by augmenting. Does that make sense? But we have to be very careful. Why? Because imagine that I use this rotation, or I use this rotation. You know, so flip. This one is totally a different number. It is 9, it's not 6. So it is not accepted, or the rotation shouldn't be, you know, the amount of degrees that you can rotate should be, for instance, between -20 to +20 kind of thing. Not 106, not 180. Okay, if you could relate to that, everything is fine so far? Okay, let's go to the next part of the explanation. It says that the goal is that at training time, your model will never see the exact same picture twice. What does it mean? It means that, Nash, I'm going to use first time, number 6, for instance, number 6, like this. Next time in next epoch, can you relate to that? In next epoch, I'm going to do another random kind of thing. So it's going to be like that. In next epoch, maybe it is like this. Okay, so the idea is if we have 20 epochs, instead of using 2000 pictures, imagine that we are dealing with 40,000, like 20 times more. But the problem is, that is my question for you guys. Are we really using 40,000 pictures, or they are very much correlated to the original 2000 pictures that we have? What is your guess? Nicholas, what do you think? Do you think that they are very much independent, or they are very much related to the original? They are very much dependent, because we have 2000 and they are just like remix of the original, right? So in that case, we are going to have high conspiracy. What should we do to cut the conspiracy? What is the trick that we use to cut the conspiracy? Do you remember? We had that. Do you have your laptop on you? So how about coming a little bit closer? Then I don't need to use, what do we call it? Megaphone, if you don't mind. So guys, Nicholas, can you hear me clearly? Okay, awesome. So what is the trick that we used, Nash? Do you remember? What did we use to cut the conspiracy? There's this one trick that Jeffrey Hinton used. You remember? Dropout, taking dropout, right? So we are going to combine them to cut that conspiracy because the images are very much related, right? Look at this one. It says that the goal is that at training time, your model will never see the exact same picture twice. This helps expose the model to more aspects of the data and generalize better. Does that make sense? So this is actually what happens. You remember that in the previous session, we started using image data generator, and we said, let's rotate 40 degrees left, right, shifting 20% towards left, right, shifting up and down 20%. Shear, what is shear? Do you remember what is shear? Okay, look at this one. I have provided this. It's a nice example. Shear is kind of distorting the picture. It's a kind of distortion towards Y or X axes, right? So flip is the easiest one. There are other kind of distortions that we could use. One of them I'm sorry, give me a sec. Yes, there we go. So you see that here we have flip, then we are going to have rotate, then we are going to have a scale, so zoom in, zoom out kind of thing, crop, and then translation. And even you could use, as you see, Gaussian noise, right? But one question that I have for you in here, you see, it mentioned something in the bottom saying fill mode nearest. What does it mean? Anyone can tell what does it mean? Fill mode nearest? Look at this picture. Imagine that we have a cat and we do any form of augmentation like tilting, shifting, or something. So we are going to have empty spaces because we did crop, we did rotation and so on, right? So do you want to leave the empty spaces blank, or do you want to make them look a little bit normal? So that is why you say, hey, fill it with the nearest pixels. So you see that it's like.
Is it just to keep like the image size the same, basically?
Yeah, it's going to fill with the nearest pixels that we have. So look at here. So it's like stretching it. Does that make sense? So that is the fill kind of thing. By saying that, let's get back to where I already explained all these parts. Look, in the code that you already have in front of you in Colab, please make sure that you are in 525 using data augmentation. Please run Shift Enter, and get to this one, Keras dot pre-processing image. And then here I say os.list directory train cats dir. What does it mean? It means that, hey, go to that directory, right? Go to that directory and use the command like dir in DOS. Show me all the files. So all the files are now inside X. If I want to show you, it's gonna, I'm sorry, I need to run Okay, one of the things, guys, my apologies, from prerequisite starts because we need all those folders that we copied the images. Please start from there. See. Just give me a second, my apologies. I need to go to another user that I'm sure everything is set there. So okay, prerequisites. There we go. And this is we have another prerequisites. Oops. Go ahead. So if you see that here, I said pre-processing. And then that's the augmentation. After that, here we have a start, prerequisite start. Can you please search for this one, this word, prerequisite? If you search prerequisite, you're gonna find it immediately. Oops. I mentioned before data augmentation. So in that case, I first relate to the operating system and I say connect to Google Drive. Based on the picture, I understood that I'm in a wrong account. So, and then saying connect. So for people at home, please make sure that you could search for prerequisite start, and that is before data augmentation. And then just quickly run all these cells. And the reason for that is first, having all directories available. And second, to make sure that you have correct number of pictures in each directory. So I'm gonna wait here for a few seconds. Whenever you could finish, please give me a signal. Done. Awesome. Jeffrey, how about you? You're doing. It's not possible to use unless that you have your account. Did you copy to your Colab on the pictures? Yeah, so you have it. Okay. In the next part, you see that image generator and plot. I go all the way to this part that I said go to Keras to pre-processing import image. And now, guys, this one, because I ran it in the previous class, but I closed the file, so I needed to go through all those prerequisites. So now I have all the file names inside X. If I uncomment it, look at the result. It's going to show you all the files inside cat from cat.0.jpg all the way to 999. You see that the last file is here, right? But I don't want to show you everything. Nash, you got it, right? That this one is going to just get the directory, the list of files. Let's comment that again, so it's not going to occupy very much of our screen. But look at the next command. I said for every file inside X, for every A inside X, just print A. And then I said, if A is equal to cat.5.jpg, just break. Otherwise, it's going to go all the way to the end, right? So if you run, it's going to show you cat 0 all the way to 5. Look at this one. When we say my f names equal to this, what actually happens, it is going to concatenate the train cats directory with the file names. What does it mean? Do you remember the train cats is this? It's the folder named cats, inside train, inside cats and dogs. Okay? And it is going to concatenate them with all the files that I have already generated. All the file names that I generate. Okay, look. I said if the file name is equal to fourth one, just break. Don't go further. Otherwise, it's going to show you everything. Why I did that, I just wanted to show you what is inside f names. So technically, if you say, show me the index number 3, guys, what is going to be inside index number 3? Nicholas, 0 is going to be file cat 0. 1 is going to be cat 1, 2, and 3. And there, I was like, oh, sorry. I said, not a bad idea to see what command I can use to just show the image. And that is the cat number 3. I load the picture of the cat. Then I said, let's go to the next phase and do the target size 150 by 150. Do you see the difference between these two? Jeffrey, do you see? Here. It is like rectangle, but it came to a kind of a square shape. Right, Said? Yeah. So this is the impact of 100, 100 resizing. And we are going to use it several times, so it's not a bad idea. That's why I expanded to see in every step what is happening when we do augmentation. Look at the next one. We converted to, we said converted to 150. We converted to an array. We added one dimension into it. And here I said, for batch in data augmentation that I generated a few seconds ago, keep showing me the augmented things. What does it mean? Can anybody tell what's the meaning of this cell? What are the commands and what are they responsible for? Look, image I, it's going to be, we are going to plot one image out of the current cat picture. Where did it come from? It has come from data gen flow from X. What is X? Do you remember? the X was just the picture of the cat that we created a few seconds ago. There we go. Yes. You see here, I set image path, and then we get to that image path, and we said that resize it. I go through all these commands to just decipher it. We said that go to that cat image and resize it, and then convert it to array, and then add one dimension to it. And then it is going to show you the first thing. It is going to show you an augmented version of the cat, and then goes again for the second time, because when we say data gen, it means that go to the list of the pictures. How many pictures we have selected? Only one. So going through all the pictures means that going through the same picture all over again. So it shows 4 different pictures of the cat. The reason for 4 pictures is we have a break condition. We say after 4 times, just break. Anybody remembers the generator? Do you remember, Nash? The generator means, for instance, if you have 10 pictures and you say go through the pictures, it's going to pick the first image, second image, third, all the way to the 10th. But when it is done, it's not going to say goodbye. It's going to get to the first image again. It's like infinite. When you have one picture and you have generator, it's going to show you the same picture all over again. So by saying after 4 times break means that you show the augmented version of the picture once, then twice, then 3 times, then 4 times. After 4, break. Does that make sense? Look at this one. I ran the code again intentionally. And this is going to give me another random set of pictures from the same subject, right? Just look at that, and then you can run it yourself too. Every time that you run, the random pictures, they're gonna just show, did I run all the things? No, I should be 0. Okay, look at this one. Here, it's going to be totally different random cats. And now remember, 2 of them they look towards right, 2 of them look towards left. I run it again and see totally different. So you see left, right, left, left, and crop happened in the last one. Okay, Nicholas, did you get what is happening here? Let's have a drawn view, kind of high-level view. What is data gen? Najib, help me. What is data gen? Data gen is it's a truck that is going to take picture and hammer it and change the shape, yes, the size, so do all those things. Is it fine so far? Awesome. So now I have that data, and I said you can play between 0 to 40 minus plus degrees. You can 20% go towards left, right, all those kind of things. And then after that, I introduced look at here. I introduced that go to train cat directory. And for every file inside there, just connect that file to the path. So we are going to have things like this. Does that make sense, Nicholas? And then I said, pick the third one, which is going to be index number 3, which is going to be this one, right? And I said, okay, show that third one. Look at that image path. I said, show that to me. And here, I said, use the resizing. So you can just see the impact. And then after that, here is the major part. Do you remember the data gen I showed a few seconds ago? That hammer kind of thing. So we say that get the picture. And what is the batch size? 1 picture. Get the picture, which is 1 cat, and the batch size is 1. And show that batch 0, because it's going to be always just 1. And then go towards this loop once again. What is this one? It says that batch data generator. Data generator is infinite. It's going to create different versions of the same picture forever. You want to say, hey, after 4 times I'm done, just finish. You say, if the remainder of the division by 4 is equal to 0, means after 4 times, just break. Finish. Does that make sense? That is why we have 4 cats. And because the augmentation is based on random numbers, every time that you run, you're going to get 4 different pictures of the same subject. Did you get it? Yeah? Okay. Let's go to the next part. What is this one? We have some layers, but there is one thing. Here we say the model is sequential. We have all those convolution layers. Then we are going to use flatten, and then we are going to use dropout. Why we use dropout? That's the question that I asked Jeffrey, if you remember at the beginning of the session. I said the pictures are very much correlated. You remember, Nicholas? I said the pictures are, because they are different, they are just remix of the original. So with that ratio, with that 50% dropout, it's a kind of very extreme. High probably, I do not allow anyone to have conspiracy, those nodes. I define compiled parameters like binary cross entropy, because cat and dog, 2 things, and Rams prop, and then metric accuracy. Here is the place, instead of saying fit, Nicholas, I use instead of saying fit, I'm gonna use fit generator, right? So be prepared that when generator is going to show up, before that, what are the things that I'm going to do? I'm going to define the train data generator. One question, Nash, do you think we need to do the same thing for validation as well? To use augmentation for validation? What do you think?
I think so.
Sorry?
Yeah, probably.
Okay, how about for test? What is the reason that we use augmentation? We just want to enhance our training. We are not gonna use augmentation because they are not real pictures, right? We want to test or validate our model based on unseen data. In that case, you're gonna make correlation on the validation side. That's what we don't want. That is why you see here we say train data gen we have augmentation, but look at this one. Test data gen, we have no augmentation. We just rescale it. Instead of having numbers between 0 to 255, we are going to just rescale it. We normalize it to a range of 0 to 1. Does that make sense? And after that, what we do is it says that train data gen, go to the dictionary. Which dictionary? Train dictionary that had cat and dogs inside, you remember? And look at this one. How many pictures you're gonna pick in every attempt? 20, right? And you're gonna just resize it. What is the class mode? Binary, cat and dog. You do the same for validation. Again, 20 pictures at a time. Here is the fit generator. I want you to search for a sec and see if fit generator still the best command that we can use. What's the answer? Actually, in 2020, if you searched for the command, you could see that there are different set of responsibilities for fit and fit generator. Now they combined it together. Sorry?
It's just in model.fit, you can just do it normally.
You can just simply, I tried it last night. So you can just simply use fit. A new version of fit uses the train generator as one of the parameters. So if it is there, well, I'm gonna just use fit generator that I had before. Else, I'm gonna use normal fit, right? So they combine these two. And tell me, what is this thingy, steps per epoch? Can anybody explain that? Why it is equal to 100 for train, but it is 50 for validation? You remember here I said the batch size is what? 20. Means every time I can pick 20. How many pictures I had in training? 2,000. Right? So I have 2,000 pictures. I have 2,000 pictures. And guess what? Every time I can pick 20, how many times I should go and pick 20 to finish all those 2,000? 100. Right? That is why we say step is 100 for that. But how many training pictures do I have? The training pictures, the number of training pictures is 1,000. 1,000 divided by 20 makes it 50. So I need to have 50 steps going there and coming back. Does that make sense? That is why the steps here is 50 because we have 1,000. The steps here is 100 because we have 2,000. Okay? Awesome. Let's go to the, and after that, when you run, look at the result. The result is magnificent. We start from, well, 50% chance, but the more that we go, it's like both of these guys, they grew up together. Okay. One of the thing is here, we created a model. What is a model? Anybody can tell what is model? Said, do you have any idea what is the model? What is the other name for model? Network as well, right? We could say network, we could say model. What is inside network, guys? Some weights and biases, right? So after training your model, what happens? Whenever you create a model, what happens? The whole thing is to put some pictures inside the model, tweak the weights and biases, make it better for prediction, the next picture, the next epoch, make some changes in biases and weights. Is it correct? So, look at this one. After you go through all those epochs, what is the result? 82% for accuracy, and for validation accuracy is 78, which is quite significant. Huh? Even one step before, we have 81, 80. Very good results. Almost no overfitting, almost, right? Here I created my model. After all these epochs, I have those weights and biases that gives me a good result. Let's save it. The old-fashioned way of saving was the file name .h5. You could just say model.save. A new version of that is model.save keras. Huh? That's a new version. There is one thing, the book has some problems. If you, for instance, use, it mentioned ACC instead of accuracy. I want to give you a hint. Whenever you face problem, go to the history, say history.keys. What is the output? It shows the name of loss and accuracy, if it is ACC or if it is complete accuracy. Okay? One more time. Whenever you face error in such command, just say history.keys. I draw a graph and the result was something like this. Please tell me, what can you infer from these two pictures? Guys, compare this one with these two. What can you infer? This is without augmentation. This is with augmentation. What can you understand from it? It's not a trick question. If you look, do you see any overfitting here on the left side? Just to tell you one thing. I watched the video that I recorded 2 years ago, exactly 6 months before the birth of ChatGPT. And almost 6, 7 people answered questions. Exactly, I asked the same question. So it's like, do you see what ChatGPT has done to you? Do you feel it? Okay. Look at this one. Here, we don't have any overfitting, and the reason for that is using augmentation. What else helped us to have no overfitting? Anybody can tell? So one, augmentation. What about the other? Jeffrey, what did I do to get this result? One was augmentation. What else? Dropout. So these two. Here I have a huge overfitting. And the reason for that is I didn't use augmentation. I didn't use dropout. Does that make sense? Okay. By saying that, we are exactly at the beginning of the next part, but I want to quickly go through what we covered on the book to make sure that I didn't miss anything. Do you see data gen here? These are the things that I have already gone through, explained to you. And these are different cats, as you see. Let me quickly, again, read this one. It says that if you train a new network using the data augmentation configuration, the network will never see the same input twice. That's the idea of having augmentation. The input it sees are still heavily intercorrelated. So to tackle that problem, what should we do? Because it says that you can't produce new information. You can only remix existing information. For tackling that problem, to further fight overfitting, you'll also add a dropout layer to your model right before the densely connected layers. And here it is, you see that the dropout. And this is very extreme way of using dropout. It's like 50%. It's a huge number. Look at this one, and that's the question that they asked you. Are we going to use augmentation for validation data? It's inside this rectangle. It mentioned that note that the validation data shouldn't be augmented. And this test data gen is what we use it here. So can I have your attention for a sec? Look at this one. In train data gen, we have augmentation. So whenever you go through the data gen train generator, you use train data gen using augmentation. But when we go to the validation, what do you use? You use test data gen, no augmentation. And then the history contains connecting train samples with train labels. Every time we are going to pick 20 pictures, and 100 times we are going to do that in every epoch. So where is the okay, here is the epoch number 100. I already told you that we go through the validation as well, 50 steps. It says that thanks to, especially emphasize, and thanks to data augmentation and dropout, we have almost no overfitting. And after that, it says by using some other modifications like regularization techniques, actually we can get close to 86 or 87, but not more. So as a next step to improve your accuracy on this problem, you'll have to use a pre-trained model. What is a pre-trained model? What do you think when you hear pre-trained model? Please search a little bit. What is the meaning of pre-trained convnet and how we can use that? Just search pre-trained convnet, how we can benefit from it. Right. Okay, so how about this? It's now 1:05. We get to this pre-trained convnet. When we come back, I'm going to explain the whole thing, how we are going to use, how we are going to reuse the convolutional neural nets. But let's enjoy 10 minutes break. Okay. Long time no see. You're totally changed. I'm just teasing you. Bruno, next break, you're gonna talk if you don't. Okay, thank you. No, not just now. Yeah. Okay, so let's continue. I asked you this question. So what is the pre-trained convnet mean? Anyone has any opinion? And how it can help? Okay, look at this one. I intentionally provided this image of cat, right? This is the first layer that the filters are very basics, and they can pick, for instance, some lines, curves, and so on. Then the more that you go higher in the hierarchy, the more abstract they would be, and they're going to help you to just get towards the label, right? Look at this. Imagine that I have something, where's the one? Oh, there we go. Imagine that we have something similar to, do you see, just trust me to save the time, I have already cut these lines before using this one, the snipping tool. Imagine that you want to use this layer for MNIST. Nash, what this guy would be look like? Which number? True. And this one is nothing but combination of these two things. Which number it looks like? This one. Well, this one.
Oh, seven, sorry?
7. How about yeah? So this is like 2. How about this one? Look at this. Number 3. How about this one? 4. So guys, you see that I just used, better to say I reused the same filters here, right? I didn't need to generate anything new. So the question that I have for you is this one. Can I reuse the same way, in the same degree, the higher levels? It doesn't look like, I can't find any number, right? So the most useful ones are in the lower part. Look at what we mentioned here. It says that a common and highly effective approach to deep learning on a small image datasets is to use a pre-trained network, or we call it, yeah, that's a pre-trained network is a saved network that was previously trained on a large dataset, typically on a large scale image classification tasks. If this original dataset is large enough and general enough, then the spatial hierarchy of features learned by the pre-trained network can effectively act as a generic model of the visual world. For instance, you might train a network on ImageNet. ImageNet is a kind of classical dataset, contains 1.4 million labeled animals in 1,000 different categories. So, and then repurpose this trained network for something as remote as identifying furniture items in the image. So you see that they are totally different, but you can reuse them. Such portability of learned features across different problems is a key advantage of deep learning compared to many older shallow learning approaches, and it makes deep learning very effective for small data problems. Okay, question. Look at the question. We have this model. Are we going to use it without anything, or are we going to use it and save the model somewhere? Do you remember I showed you how to save the model? Somebody, well, actually two people, Simonian and Zisserman, if I'm not mistaken by pronouncing the name, they used these 1.4 million labeled images and they called it VGG16. Please search for VGG16 and see what you can find, VGG16. And one of the, if you click on any of the images, look, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 3 dense layers, totally 16 layers. So that's why they call it VGG16, right? And the idea of that is having, and look at this one, it's not like the models that we created before, like conv2D, then max pooling. No, we have conv2D, max pooling, conv2D, max pooling, and then we have 3 conv2Ds and then 1 max pooling. You see that? Okay, by saying that, we get to BGG architecture, and to go to that, to use these two, we have two approaches. One of them is feature extraction, and the other one is fine tuning. And even for feature extraction, we have two approaches. So today, we can just go to feature extraction and go all the way to the end of this part. Let's see. Before anything else, let's go together and watch this short video. It's like 7-8 minutes, but it's like a review of everything that we have learned so far. So please pay good attention. Let me just check one thing before I start. Okay. One of the students asked that, is it possible that I train my own classifier and have my own data set and so on? Look at this one. Somebody decided to have 10 different fruits and vegetables, and they just used one cell phone, one mobile, and they just created their own data set. So look at this one. The gentleman just created similar network while we can simply import it. We don't need, but the gentleman decided to write these simple lines. You can do that as well. What I very much like about this presentation is you can see how these filters impact on the images. And look at this one. We have conv 1, then we have conv 1, 2. You remember we had 2 layers of convolutions in the first layer, then we had 1 max pooling. Let's see how it works. Okay, look at the parameters except hardware that mentioned and the training time. What is the batch size? 5. What is the augmentation? That's what we used. Train generator, you remember? We said that train generator, rescale it, and then did all those things. And then what is the loss? Category called cross entropy. And what is the optimizer? It's Ram's prop. Do you see that the first layer contains simple filters? You see that? And these are the results. Okay, look at this one. Here, this is super nice. From this size, whatever it is, we just get to a half size of the original. And look at the rest. And look at the filters. Don't you see that they are more sophisticated compared to the first layer? Okay, look at this one. It was, oops, sorry. It's exactly another max pooling, half the size. And look at the filters. There's quite something. Like it's not possible to pass through all these filters for all the objects that we have. At the beginning, for all the filters, we could have something like the output. But the more that we go further, we have less results. We have lots of blank because the filter doesn't let you go through, right? Another layer, convolution layer 3. this is super nice to see. So that's the first convolution. That's layer 1, 1. Look at the output, considering 32 filters that we have. Look at the filters. Now the filters are a little bit sophisticated. I very much like this. It shows lots of things to us. And the more that we go further, the more blank filter, the more blank results we have, because they cannot go through those filters. This is the next layer. Look how many blank things we have. Still layer 3. Guys, I go fast forward. Layer 4, and now we have layer 5, the last. Can you understand anything out of this? Well, if somebody shows you such a thing, can you understand if it is Apple or what? So what actually happens is, let me tell you one thing. What actually happens is, oh, we have net. Sorry, Min, I didn't check. My apologies. Show you. There we go. Okay. I just work on one of them, but Nash, imagine that we have the output of just one filter, right? Look at this one. This guy would be here. This one, imagine that the length is just 1 pixel for any of them. Would be here. The next one would be here. The next one would be here. Oopsie. And
Supposed to be like flat.
exactly. And just imagine that what I worked on was just this. And for the next one, I'm gonna do the same. For the next one, I'm gonna do the same. For this next one, I'm gonna do the same, and make one string. And what is the length of that string? Please multiply 4 by 4 by 512. It's almost 8,000 something. Look. So technically 16 times 512, almost 8,200, close to that. 8,192, but where that number come from? If you just go to the architecture of the layers that VGG16 provides for us, look at the last layer. We have 4 by 4 by 512. So we applied all those filters. We have one string that contains that number of pixels, 8,000. And imagine that 8,000, the one that I showed you, imagine that this one is just 16 pixels, 4 by 4. Imagine that we have another one. Guys, I'm lazy, I can't. Imagine that we have another one and another one and another one. So what are the number of things? 8,000 some hundreds. Then you are going to use it as the input of densely connected layers. Does that make sense? Okay. Look at this. Let's read quickly this part. It says that feature extraction consists of using the representation learned by a previous network to extract interesting features from new samples. Okay. As you saw previously, ConvNets used for image classification comprise two parts. What are the two parts? One is convolutional and the other one is densely connected. You see that we have convolutional and densely connected. In other words, if you can just see in any of these examples, we have convolutional, and after that we have densely connected. Okay. It says the first part is called the convolutional base of the model. In the case of ConvNets, feature extraction consists of taking the convolutional base of a previously trained network, running the new data through it, and training a new classifier on top of the output. So from this one, what can we infer? Spend 1-2 minutes. See, and that's not a trick question. It's a very simple thing. What is happening here? I'm gonna bring this one close to the neighbor that can help you and gives you some ideas. Okay, what can we understand from it? First thing first, Nash, do you think that these are not trick questions, guys? Do you think that the usefulness of this layer is similar to the usefulness of this layer?
Feel like it might be.
The lower one is more useful because there are more generics, right? So, and if we go higher and higher, in densely connected layers, the position of where, for instance, that digit numbers, the number 6 exists on the screen is important. So in that case, I cannot use pre-trained network to find the location of a new digit or new object, which is not digits, using the densely connected layers. That's the first thing. So it's not general. It is very spatial intensive. In that case, the best that we can do is just learn the convolutional filters that is here and freeze them. And then we plug the densely connected layers on top of it. Imagine that this is 1.4 million picture data set, and we trained it using the convolutional network, and then we plug the densely connected on top of it, but this one is not reusable, so forget it. You're gonna just use that part, the convolution, and then we plug the densely connected layer on top of it. The question is why we say frozen here? Why we use frozen? Anyone has any idea? Yes?
Because it would change or stay the same.
Pardon me?
This was like, there'll be no changes, it'll be stay the.
Why we don't want to change it? That's the first question, because the idea is just tweaking weights and biases, right? To modifying it to get better results. Okay, remember at the beginning, what would be the values that we have for weights and biases? Are they calculated or they are random? Just search about it for a sec. So guys, what are we going to do? We use random numbers, and those random numbers are at the beginning are crazy. If we do not freeze it based on the back propagation, it is going to give kind of crazy results. It's going to change all the weights and biases in pre-trained network. Technically, it destroys the pre-trained network. We don't want that. We want to use it, right? So for doing that, we just freeze this part. So this frozen part is actually the convolutional layer. And then we just modify the weights and biases of the densely connected layers. Does that make sense? Once again, because at the beginning, we have just random numbers, random weights and biases. Based on the very off results that we have at the beginning, it's going to propagate all the modifications towards the convolutional layers as well. So it destroys that. And let's just read this part for you. The first part is called the convolutional base, we said. And in the case of convnets, feature extraction consists of taking the convolutional base of a previously trained network, running the new data through it, and training a new classifier on top of the output. But you see that we have some circles here and there. It shows that that's super important. I read it for you. It says that why only reuse the convolutional base? It said, could you reuse the densely connected classifier as well? In general, doing so should be avoided. It's better not to, even if they are very close. Representations learned by the convolutional base are likely to be more generic. Do you remember that I asked Nicholas that question and I said more generic and therefore more reusable? Imagine that the feature maps of convnets are presence maps of generic concepts over a picture, which is likely to be useful regardless of the computer vision problem at hand, but the representations learned by the classifier will necessarily be specific to the set of class on which the model was trained. They will only contain information about the presence probability of this or that class in the entire picture. This is what really need to be considered. Additionally, representations found in the densely connected layers no longer contain any information about where objects are. So in the input image, we don't know any idea about the position of the objects. That is why these layers get rid of the notion of a space, whereas the object location is still described by convolutional feature maps. For problems where object locations matters, densely connected features are largely useless. Look at this one. Again, this is super important. Layers that come earlier in the model extract local, highly generic maps, such as visual edges, colors, and textures. Just remember this example. The first generic, you remember that we talked, they are more generics, so we could use them. And then look at the reusability of that layer. And in the next part, it says that if your new data set differs a lot from the data set on which the original model was trained, you may be better off using only first few layers of the models to do feature extractions. This is something that we are going to use in fine tuning. Look at this one. Nash, do you think that we could use this one too? Isn't it better just to use this layer and forget about this for something like MNIST? I guess so, right?
Yeah.
So the ideal situation is when we can freeze. And when I'm talking about that, look at this. I'm sorry. You see, if we have different convolution layers, imagine we are gonna keep the first four. You remember we had conv2d, max pooling, then something like that. So we are going to keep the first 1, 2, 3, 4 blocks, but just we are gonna modify the last conv2d blocks. Does that make sense? So getting back to here, it says that let's put in practice by using the convolutional base of VGG60 network trained on ImageNet. And we are going to use that for dog versus cat classifier. This is something that, did I copy this one? We are going to use this a lot. Okay, I'm going to use this one here, and I'm going to copy that. You're going to see why in no time. Okay. What can we understand from these lines of code? It says that we use VGG model. What we are going to use is going to be ImageNet. ImageNet is that 1.4 million data set. What does it mean saying include top equal to false? Look at here. It means that we are going just to freeze just to use the convolutional part, and let's get rid of the densely connected layers. It's mentioned here, like refers to including or not the densely connected classifiers on top of the network, those 3 layers that we had on top. By default, these densely connected classifiers corresponds to the 1000 classes from ImageNet because you intend to use your own densely connected classifiers like cat and dog, you don't need that. Okay. So how about the input shape here? If you don't mention it, it's going to accept any size, and the burden is on the shoulder of the computer. But if you say that input shape is 150, 150, and 3 channels, one less job to think of for computer. So the input shape is the shape of the image tensors that you'll fit into the network. If you don't pass it, the network will be able to process input of any size, but one more task, right? Look at this one. Just the convolution part provides something like 14,700,000, close to 15 million parameters. Can you imagine? It's huge. It's a huge number. For MNIST, remember that we had just something like 32K. This one is like 500 more parameters. So we get to the part that, okay, what are the ways that we can reuse this? Let's have, it's now 1:53. Let's have a 10-minute break. And we are going to come back and answer this question by saying that how we can use, guys, remember the last layer is 4 the size of the window and 512. That's the last layer. So it says that the final feature map has this shape, and that's the feature map, a feature on top of which you'll stick a densely connected classifier. At this point, there are 2 ways you could proceed, and we're going to talk about those 2 options right after the 10-minute break. We're going to continue at 2:05.
Yeah. No, it's just posted on the site. I was like, okay, so I'm just looking at it. We need to yeah, I'm gonna go and do it. I'll just figure out what you want to do. I thought it was gonna be way harder than that. He actually goes a lot simpler. It's like he said something about like we're gonna have to do API calls and do that. Yeah. Is he saying something like, did he start with anything? Well, you don't. That's with Flutter, right? He just goes too fast. Right. So he's lost. At the time, almost like, well, sometimes we'll get lucky and we'll be watching the recording. Because they're just like, just doubling up the time. Yeah. last week I just gave up. Or it was week before, the week before, you was doing that GPS thing, the other app, like halfway through, you just hammering through them. And they already finished an hour and just left, and we're like sitting there like, okay. Just left the code open, as you can, you didn't log out of the computer, and it was like, alright.
The good thing is last week, the lab was needed.
Yeah. I think the one that he's doing today, needs to do something. Don't work on it, project. You know, like, so two views, like the base of the software, so implementing for the city and the past and for. That's either like, you or like, it will show like, you get the testing sorted, in progress, and then just have a little thing to decide if they want to make it. You don't have to go like it. And then we decide. Better. You don't seem to care. Like it works. So weird, honestly. I feel like most of the apple's done last like part of it, right?
Honestly, I'm not thinking this class is the.
I don't know. I don't think see myself ever being an iOS developer. I hate Xcode and I hate sweating. I hate telling that. Xcode is the what's like unnecessary, like you know, I added you know, like those drop down menus, so we have the little rotating ones on iOS. I did that, the amount of code I had that add, it was like three functions and all this stuff, like a bunch of variables, and I'm like, oh, like just to sway through like Android, it's like you make all this. You just like set it to that basically the drop down menu. I'm like, how hard is this? Or like a switch case or something, and this one.
I remember you showing us with
Yeah. That's just crazy. And I love how he taught us core data the week after we had it. I was like, bro, I sat there for like hours, like figuring everything out. And you teach us the week after a project.
Okay, so now is the time. I told you that there are two approaches for reusing a network. One of them is running the convolutional base over your data set. Look at this one. It means that we have pictures. We run the convolutional part, those combination of max, pulling, and conv2d. And then we are gonna have filters. How many times we are gonna do that, Nicholas, you think? How many times we need to, if we just want to bring it as the input of this network, comprise all these steps, and receive those kind of things. For picture one, I'm going to bring it to all these steps and make what? Make 8,192 cells. Just I'm gonna do it once. Does that make sense? For picture number two, I fit it here and I'm gonna have 8,192 cells again. And for picture number, long story short, look at this. It says that running the convolutional base over your data set, recording its output to a NumPy array on disk, and then using this data as the input to a standalone densely connected classifier, similar to those you saw in part one of this book. So after that, instead of having pictures, you're going to have filtered pictures that are 8,192 pixels. Does that make sense? This solution is fast because of what? Why it is fast? Because the most time consuming part is convolutional part, is this part. And you are going to bring all those pictures once through this network. And after you are done with that, look, this solution is fast and cheap to run because it only requires running the convolutional base once for every input image. And the convolution base is by far the most expensive part of the pipeline. But there is one problem. Question for you. When did I use augmentation? Do you have any idea? When augmentation happened? Augmentation happened in convolutional neural nets, right? In that case, because you don't have convolution, look, this technique won't allow you to use data augmentation. So data augmentation never happens through that because augmentation happens through the convolution. In this approach, we go through the images once through the convolutional base, and then, for instance, we are going to go through 30 epochs. Nash, look at this picture. Just we have those pictures, and then we are going to have those filtered 8,000 something. The epochs happens in here, in densely connected layers. Does that make sense? And this is not very much time consuming. This is one approach. The second approach is this one. In this one, we bring the pictures from end to end epoch. We are gonna go through all those things. Then we are gonna go after that, after those filters, all the way to the result. This is gonna be just epoch one. And epoch two, we go through all these convolutional parts once again. So technically, it's gonna take forever. That's why I told you, if you run the second, and today we don't have time to work on that part, but if you spend time, it's gonna take something like 8 hours. That's not a joke, 8 hours to go through end to end. Okay, so let's go to this one. I want you to read this for a second and tell me if you can understand everything out of it. It says, extending the model you have by adding dense layers on top and running the whole, means the convolution and dense layer end to end on the input data. This will allow you to use data augmentation. So now we have this chance. It is going to add more time to our computation time. So because every input image goes through the convolution base every time, it's seen by the model. But for the same reason, this technique is more expensive than the first one. Look at this one. It says that recording the output of conv base on your data and using these outputs as the inputs to a new model is what you're going to do. So in every single epoch, we are going to have one version, one remix of the original picture. Okay. Guys, do you see this algorithm here? This is the first one, the fast approach. It says that the fast feature extraction without data augmentation. And here it says that you'll extract features from these image by calling the predict method of the conv base model. I can't understand this. And do you see the algorithm? It contains 2 pages. Let me tell you one thing. Read this one, understand it and explain it, and you don't need to come to final test. You have full mark for final test. This page, all the way to this. Page 147 and page 148. You have 5. Any idea? Okay. Last minute. Can I have your attention? Everybody, time is up. See you all in the exam. Look, this part is super easy, so you don't need to. We import some libraries. Also, image data generator, because we want to go through all the pictures, right? Look at this one. What are these directories? Can anybody tell? The first one is where we can find cat and dogs. That's the base directory. We have train, we have validation, and we have test directory. We just need to join them, right? We need to join validation at the end of cat and dogs to get the validation directory. You remember that, right? Just to show you something. Okay, if I go to the Google Drive, you remember I created chapter 5 folder and it contains cat and dog small. Look, in the train, for example, we have cat and dog, but when I say go to the train, generator is going to find the folders by itself. You don't need to bother. Anyway, what is this one? Guys, do we have train data generator and test data generator like what we had a few seconds ago in here? Do you remember? In here, we had train data gen and we had test data gen. But because we can't have augmentation, we are going to only have only data generator. We don't say any of those augmentation. We say that just normalize it by dividing by 250. What about the batch size? Every time go and pick 20 pictures. And then we say, this is the extract features. We go to the directory. What is the sample, number of samples? Donald, what is the number of samples for training? Do you remember? 2,000. So we had 2,000 pictures, 1,000 cat, 1,000 dog. And then in that train directory. How about this one, sample count? So definitely it is going to get that number. And we need to create 4 by 4 by 512, the last layer of conv2d. Cells, we initialize them with 0. We create features ready. Any picture that we enter here, any picture that we enter, it is going to provide 8,192 cells. We create that ready in here. What about the next? We are going to have 2000 labels as well, right? For every picture, we are going to have one label. How about this generator? We say that, okay, data gen, go to the directory that we have set. It could be either train, validation, or test. Go to there. If it is train, then well, the target size is 150, 150, that's rescaling. And then the batch size is 20, that's where we assign. And it's gonna be binary. Look at this part. We are gonna say the first time from the generator, guys, from the first time in the generator, and if you want, you can just see generator here and there. Let me just link them so easily you can find comments. Where is the draw? Okay. Or is it possible to use this one? So I think that's the best is using simple line. Yeah. This generator actually, we go through it every 20 pictures that we have. And then here we are going to consider I from 0 all the way to 100 it should go. Every time it picks 20 picture, first time. What is I first time? Donald. What is the I value in the first time? Awesome. So it's gonna be 0 multiply 20 all the way to 1 multiply 20. So it's gonna be from 0 to 19. We get the feature batch because it goes to first 20 and we place it into features that we have. And then we assign the labels to the first 20. And then we add 1 into I. What is I next round? Awesome. So it's going to be 1. Is 1 multiply 20 greater than 2000? Not yet. So we are going to go to the loop. We pick the next 20 pictures. Look at this one. What is happening here? This is the goal of the whole algorithm. That's why I said this is super important. Do you see that it says that conv base? Remember, I copied everything into whiteboard to show you. The conv base means that bring everything to, I'm sorry, bring everything to that VGG16 and apply the network into it. So we are going to put picture, we apply that predict, and it is going to apply everything from VGG 16. And now we have the result inside feature batch. So take the first 20, apply VGG 16, and then place it in the first 20. And then do the same thing for the next 20 picture, and do the same thing for the next 20 picture, and so on, all the way to 2000. And that is for training, right? Here in this place, we call this function for train directory, and we have 2000 over there. Next, we are going to use the same function, extract features for validation directory, 1000 we have. And finally, we are going to use the same thing for test, and we have 1000 there. Does that make sense? Look what we have mentioned here. We said we make the features ready here, and we predict its values using the conv base predict input batch. And what about this one? We go to the generator process every time we take 20 images. and that's batch size, and we bring those 20 images into conv base predict and get the result of the convolutional process in the features batch. Every step, we add 20 of the results of the features batch to the features. We fill the labels as well. We continue this process as long as I batch size is less than the overall image size. So 2000 is for just training. What is happening here? That is simple. Anybody can recall this? Uh-huh. We have those train features like 2004, 512. Instead of that, we are going to have 2000 4 times. Do you remember the time that we had 28 by 28 pixels for MNIST? Exactly like 25 times 25. Here we say 4 times 512. So it's kind of flattening. And we do the same thing for, what do we call it? For the visual validation, and we do the same thing for test. And this part is as simple as what we learned for MNIST, having a sequential layer. How many dense layer we have here? How many hidden layer we have in this example? Donald, you're the only person who can be teased. Okay, how many hidden layer? Awesome. So here we say that we have 256 and the activation is value. The input is that 8,192. So or 4 times 512. And the dropout is kind of crazy. It's very kind of extreme. And then we say that the activation for the last layer is sigmoid Y because we have cat and dog. We have binary. If it was, for instance, different animals, we could use softmax. And then we have compile. We have those parameters, and then we say fit. And for the fit, what we are going to pass the train features, the train labels. And here it is going to just show the, oopsie, let me just bring here. Okay, it says that training is very fast. Why it is fast? Because we do not spend time on convolution. And because you only have to deal with 2 dense layers, right? One of them is hidden layer. And if you see, it is going to give you this output. I want you to think about this output and compare it to the previous one. What can you infer from this compared to the previous one? And I'm gonna bring it for you to the convolution that we had. This is the last task that we have. What can you understand from this? Well, let's not talk about the epochs because they are different in that terms. This one is 100, this one is 30. But what can we understand from it is we have vivid overfitting here. Does that make sense? The overfitting in here is huge kind of thing. But we don't have any overfitting. How about the accuracy? Is the accuracy higher compared to this one? Yeah, it is higher because here we have almost something like 80, but here the accuracy is close to 90, right? It's 82, 83, but here we have 90. How about the loss? The loss, if you compare, don't be deceived by this. It is 0.7. It's super high. But here it starts from 0.5 and drastically decreased to 0.3. And even right off the bat, we are going to experience the overfitting. And just in epoch 2, we have overfitting. So what can we do? What is the factor that helps us not to have overfitting here, but we experience it here? Anybody can tell? What did we use here that help us not to have overfitting? Augmentation, data augmentation. Here we use data augmentation and dropout. Here we didn't use augmentation, we reused models. We used extracting features from trained model, right? But this is approach A. Approach B gives us the ability to have augmentation as well. So that part is the part that we are going to take care of next week. So by saying that, let me just quickly read this one. It says that the plots also indicates that you're overfitting almost from the start. Despite using dropout, so it means that dropout helps, but it couldn't help like what we had there. So the major factor was data augmentation. Despite using dropout with a fairly large rate, means 50%, we had that overfitting. That's because the technique doesn't use data augmentation. So next, we are going to combine feature extraction and augmentation. And the result is crazy. The result is super high and, as you see, very reliable. So next week, we are going to continue from where we left off, and that is feature extraction with data augmentation. By saying that, let's just check the chat. Malik, we waited a lot. Hopefully, we are going to see you soon. Okay, guys, I'm going to stop sharing and stop recording. Thank you very much. Have a good one.